Today we're going to be talking about how to find parametric equations for the line of intersection of two planes. And in this particular problem, we've been given the equations of two planes. One is x plus y plus z equals 1. The other plane is x plus 2y plus 2z is equal to 1. These planes, we've been told, intersect one another, and when they come together, the intersection forms a line. What we want to do is find the equation of that line, and more specifically, we need to find parametric equations that define that line. So in order to do that, in order to find those parametric equations, we need two things. We need the cross product of the normal vectors of each of these planes, and we need a point on the line. So the first thing we need to do is find the normal vector to each of these planes, and the way that we do that is by taking the coefficients on the x, y, and z terms and combining them to form the components of the normal vector. So in our first plane here, we have coefficients of 1, 1, and 1, right? We have 1x plus 1y plus 1z. When we take those component values, we get a normal vector of 1, 1, 1 for this plane. Similarly, over here for the second plane, if we take our coefficients, then our components become 1, 2, and 2. These vectors are vector representations of the normal lines for these planes. So our next step is to take the cross product of these normal vectors. We'll call this normal vector A, and we'll call this normal vector B. So we're going to take the cross product of A and B, and that's going to be equal to our 3x3 matrix that we always use to find the cross product, where in the first row we put I, J, and K. In the second row we put our vector A, 1, 1, 1, and in the third row we put our vector B, which is 1, 2, 2. And if you're familiar with the cross product, you know that we need to break this down into its discriminant parts. So we're going to start with our upper left-hand corner, which is I, and we're going to multiply that by the 2x2 matrix, which is formed by taking everything that's not in the same row as I and not in the same column as I. So that's these four values right here that are not in the same row or column as I. We're going to take those in exactly the same format they're in and put them over here in a 2x2 matrix. So we've got 1, 1, 2, 2, and we're going to multiply that by I. We need to do the same thing for J and K. The only difference is we need to remember that we're alternating signs each time we do I, J, and K. So we start with a positive sign for I. So this term here is positive. Essentially, there's a plus sign out in front here. This is a positive term. Then we're going to have a negative term for J and a positive term for K. So now for J, we're going to take J times everything that's not in the same row and column as J, which is going to be these two 1s right here, and this 1 and 2 right here. So putting those into a 2x2 matrix, we're going to say minus, because we have this minus sign here. Now we have the 2x2 matrix 1, 1, 1, 2, and multiply that by J. Now we have a positive sign here for K, so we're going to say plus the 2x2 matrix, everything that's not in the same row and column as K, which are these four numbers over here, 1, 1, and 1, 2. So our 2x2 matrix looks like 1, 1, 1, 2, multiplied by K. Now all we need to do to simplify this, when we have a 2x2 matrix, we multiply the upper left-hand corner by the lower right-hand corner, so 1 times 2 here is 2. And then we subtract the product of the lower left-hand corner and the upper right, so 2 times 1 is 2, so we've got 2 minus 2 times I. Now here for J, we do the same thing. 1 times 2 is 2, minus 1 times 1 is 1, multiplied by J. And then for K, we've got 1 times 2, which is 2, minus 1 times 1, which is 1, multiplied by K. When we simplify, you can see 2 minus 2 will get 0, so we're going to get 0I. For J, we've got 2 minus 1, which is 1. We have this minus sign in front, so we're going to get minus 1 times J, and then 2 minus 1, which is 1, so we'll get plus 1K. If we simplify here, this is going to become two things. Obviously, 0I is going to disappear. We're just going to be left with negative J plus K, but we can also put this in vector form by taking these three coefficients. We get 0, negative 1, positive 1. Now remember we said before that in order to find parametric equations, we needed the cross product of our two normal vectors, which we now have. That's the vector 0, -1, 1. And we also need a point on the line. Well, the way that we're going to find a point on the line is we're going to set z equal to 0 in both of these plane equations. That's going to eliminate the z variable. We're only going to be left with x and y. That'll allow us to solve for x and y values when z is equal to 0, and it'll allow us to find our coordinate point. So when we set z equal to 0 in both of these equations, here's what we end up with. For our first plane, we've got x plus y plus z equals 1, or x plus y plus 0 equals 1, and that's just going to simplify, of course, to x plus y equals 1. For our second plane, same thing here. 2 times 0 is going to give us 0. That term's going to drop away, and we're just going to be left with x plus 2y is equal to 1. Now we're looking to solve this system of simultaneous equations. An easy way to do it is to subtract the second equation from the first one, because when we do that, notice that we'll get here x minus x, or just 0, so our x variable goes away. We'll just be left with a y variable. Y minus a 2y is going to give us -y, and over here on the right, 1 minus 1 is going to give us 0. If we multiply both sides by -1, we see that we get y is equal to 0. So we know for our coordinate point that our z-coordinate is 0 because we set z equal to 0 in both equations. We now have the y value, which we know is also 0. All we need to do is plug in this y value of 0 into one of these equations to get the x value. So here we'll get x plus 0 equals 1 when we plug 0 in for y. And of course we can see then that we get x equals 1. That means that our coordinate point then is our x value, which is 1, our y value, which is 0, and our z value, which is 0 because we plugged in 0 for z to both of these plane equations. So now we have here our coordinate point and the cross product of our normal vectors. Those are the only two things we need. So let me show you how you're going to use those to write the parametric equations that define the line of intersection between these two planes. Here's what we're going to do. We're going to take first the values in our coordinate point. So in our case, the x value in the coordinate point is this value of 1 right here. So we're going to take that value first. We're going to get 1. Then we're going to add to that this value from the cross product of our normal vectors. So in the case of x here, that's 0. 0 times a parameter t. So we're going to take this x value of 0 and we're going to multiply that by the parameter t. This is going to become the coefficient on our I component. And we're going to pair each of these components together and do the same thing for j and k. So we're going to take our y components, first the y value from our coordinate point here, which is 0. Then we're going to add to that the y component from this vector, which is -1, times our parameter value of t. And this whole thing is going to become the coefficient on j. Now we do the same thing for k. We take the z value from our coordinate point, which is 0. We add to that the z value from our vector here, which is 1. We multiply 1 by our parameter value, t, and then we multiply that by k. That whole thing becomes the coefficient on k. When we simplify this, we're most concerned with the coefficients on I, j, and k. So 1 plus 0t is just going to become 1 in front of the I. So we're going to get 1 times I. For j here, this 0 is going to go away. We're just going to be left with -1t or -t. So we'll say plus a -t times j. I just want to keep these coefficients isolated like this. So -t times j. And then for k here, 0 plus 1t is just going to simplify to t. So we're going to get plus t times k. Now the reason I was so interested in keeping these coefficients isolated in front of I, j, and k is because these coefficients are going to become our parametric equations for the line of intersection between the two planes. So we're going to grab these three coefficients here and set them equal to x, y, and z for I, j, and k respectively. So x, y, and z is how these correspond with one another. So for x, we're going to say x is equal to 1. For y, we're going to say y is equal to -t. And for z, we're going to say z is equal to +t. These three together form the parametric equations of the line of intersection between the two planes. Now, the only other thing that we can do in this video, because sometimes we're asked to find the angle between the two planes, and we can do that easily. All we need is our corollary formula for cosine of theta, which we use frequently to find the angle between two planes or two lines when it comes to vectors. So we've got cosine of theta here is equal to, all we need to do is the dot product of A and B. So we have our normal vectors to the planes here, A and B. We need the dot product here. And remember that the dot product is taking the sum of the product of each of our components here. So we're going to take 1 and multiply it by 1 here. So 1 times 1 is 1. Then we're going to add to that the product of our y components. So 1 times 2 is 2. And then add to that the product of our z components. 1 times 2 is 2, so we'll say plus 2. Then we divide that by the magnitude of A times the magnitude of B, remembering that magnitude is essentially the same as the length of both of these vectors. The way that we find the length of the vector when we've got the vector in this form, all we do is say the square root, and this comes directly from the distance formula in 3 variables. We just take the square root here of each of these direction numbers, added together and squared, or I should say squared and added together. So 1 squared is 1, plus 1 squared here is 1, plus 1 squared, this number here, is 1. So that is the magnitude of A. The magnitude of B is going to be 1 squared is 1, plus 2 squared is 4, plus 2 squared is 4, so plus 4. And now I just need to solve for theta. Here's what that's going to look like. Cosine of theta is equal to 1 plus 2 plus 2 in the numerator is 5, divided by, in my denominator, square root of 3 times 1 plus 4 is 9, so square root of 9. Now I just need to solve for theta. I do that by taking the inverse cosine function, or arc cos, of both sides. That'll cancel the cosine from the left-hand side, leaving me only with theta, which is the angle I want. So I'll get theta is equal to arc cosine, or the inverse cosine function, sometimes we write it cosine to the negative 1, of 5 divided by square root 3 times square root 9, which is really just square root 27, like this. And I would plug this into my calculator to find theta. Now, one important note, if you're going to plug this into your calculator, it's very important that you set your calculator to degree mode in order to get the correct answer here. If I set it to degree mode and plug it into my calculator, I'm going to get an answer of approximately 15.8 degrees, which is what I want. If it's in radian mode, you won't get the right answer. Normally we want our calculators in radian mode, but in this case, when you're looking for the angle between two planes or two lines when we're dealing with vectors, we want it in degree mode. So take the inverse cosine of 5 over root 27, you should get approximately 15.8 degrees, which is the angle between these two planes.